Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be discussing model accuracy, stability, and sensitivity. As you see here, I've got the user's manual up on the screen, and I will leave a link to this page in the video description so you can follow along if you'd like. First, a few definitions. In order to develop a good unsteady flow model, the user must understand how and why their model becomes unstable. This knowledge will help them figure out how to fix the problem and obtain good results. Further down, there's a definition for model accuracy. It basically says the accuracy is defined by the degree of closeness of the model results compared to the true solution. And that's based on a number of assumptions here, such as the geometric data, the flow data, the equations used by HEC RAS, as well as any other assumptions. Below that, we have the definition of model stability. Model stability refers to the model's ability to produce consistent, physically realistic results without any oscillations or divergence as it solves its governing equations. What you see here in this plot here is an unsteady computation. Yes, it looks like the computation finished, but there's a number of different oscillations throughout the compute. And then further down below that, here are 13 factors that affect stability and the numerical accuracy of the model. So we have cross-section spacing, that's a big one. Computation time step, that's another big one. In fact, I'd say these first two are perhaps the two most important, the two that you may want to most likely look into first. Theta weighting factor, calculation options and tolerances, lateral structures and weirs, and so on, all the way down to 13. And just below that, there's another part of the user's manual that talks about finding and fixing model stability problems. So we're going to look into this link right here, which is my next tab over, and then as well as modifying cross-section spacing and computation time step. All right, so I have a model right here up and running in HEC RAS. It is a single river reach that's 10,000 feet long, and it is a slope of 1%. So what I have, let's go ahead and just show the cross section. Here's that. And then I have my flow data. So this is unsteady flow. Here is the flow hydrograph right here. It starts at about 20,000 CFS, ramps up to almost 600,000 CFS, and then back down to 20,000 CFS. So I'm going to go ahead and just run this simulation. We got cross sections every 1,000 feet here. And close that, and then unsteady flow, and then click compute. So I'm just going to let the recording run and show you what it looks like at the end of a compute. We had some red text pass by, so I'm just going to scroll up in this computation messages text box a little bit. And what we see is an error message, or this is really a warning. River A, reach 1, that's my reach. At River Station, 10,000 down to 2,000. So that's basically the entire reach. We had a volume accounting error of 3,664 acre feet. That's 0.29%. Please review the computational log file and volume accounting details. Now that right there looks bad, but it's kind of hard to evaluate just how bad the error is and what sort of instability we're dealing with. So what I'm going to do is what I typically do to take a look at some of the results like cross sections, water surface profiles, stage and flow hydrographs, and so on. Let's go ahead and just position ourselves halfway down the reach at River Station 5,000 and then run the animation and see what this looks like. So far, so good. And then we go crazy. So this looks wild. You can see in the mini map that if I right click and click full plot, we're basically 200 feet underwater, which is unrealistic. This channel should not have any problem conveying this flow. Also, if I go view water surface profile, this is what I mean. This is unrealistic because the cross section itself right here is probably 60 feet deep max. Well, the main channel is only 30 feet deep, but then another 30 feet for the overbank, 60 feet, not 200 feet, which is what we're seeing here. In fact, I think I can just measure the depth if I hold down control and then a single left click and then drag down and then let go control. There we go. Okay, so that's 185 feet, but this is not the time step of the highest depth anyway. If I go to animate from this profile plot, you'll see what I'm talking about. This is clearly not a stable model, nothing you'd want to actually use without fixing. All right, so let's go ahead and fix that. If I have the unsteady flow analysis dialog box open right here, I can click on options and then view runtime messages. These are just the same messages that we saw pass by us during the compute routine. So if for some reason you close the window, but you wanted to access those notes again, there you go. And then the option just above that is options, view computational log file. This text box doesn't have a whole lot of information, and that's only because we didn't tell it to write out much information. But once we have a problem with our model and we want to export more data, this is the file where we would find it. And to export more data or, debugging notes during the compute, we can come up to options, output options. We're going to look at the detailed log output and computation level output options. So first is the detailed log output. We can echo out the input hydrograph and the computed hydrographs. So I'll just go ahead and do that real quick so you can see what it looks like. What we're seeing on this screen will be the exact same as before. So nothing new there. Close. But now if I go to options and then view computed log file, here's the inflow hydrograph at the cross section at the top of our river reach, which is river station 10,000. And then down below that, I'm going to get all sorts of notes that talk about water surface elevation, the reach, the time period, and so on. I'm not going to analyze this right now because there's just too much to talk about. And I also want to demonstrate a few other outputs. Options, let's go back to that output options, detail log output tab. I'm going to check off that hydrograph. We can write the initial conditions, or if we know the specific time step that there's a problem or time steps, we can go and specify that right in here. So I'll check that on. I'll say this is from January 1st, starting at 3 a.m. And then that would go to until 5 a.m. right there. So let's just go ahead and see what that looks like. Okay, save and run. Okay, once that's ran again, we can click close, options, and then view computation log file. We can scroll back up to the top to see the original data, but then now down below we have some different data. So starting at 3 hours, or actually I scrolled down too far. Here we go. Starting at 3 hours until 3 hours and 1 minute. This 3.01677 hours is just 3 hours and 1 minute in hours decimal format. Then we have information about river station 8,000, it looks like, the water surface elevation, and so on. So as before, I'm not going to go into too much details. We have some other warnings right down here. Okay, so I'm going to close that. And then in options, output options again, detailed output. Let me check that off and then head over to the next tab over, which is computation level output options. Here, what I could do is select write computation level output file and then select the different variables that I want, such as water surface air, flow air, depth, invert, and so on. I'm going to leave a few of these unchecked just so you can see what checking the box does. But right now, if I go up to the view menu, actually, I guess I have to close this. If I go view, then the unsteady flow spatial plot and unsteady flow time series plot are grayed out. And that's because I have not last ran the model with this output option enabled. So let me go options again, output, computation level output options, check this checkbox, and then, yeah, let me check these fields on, leave a few off. If you know exactly what time period, you can specify that in this date time text boxes, but I'm just going to let it run for the entire simulation and we'll see what that looks like. So I'll click OK, file, save, and then run. This may take a little bit longer in the post-processing step. Okay, no, it didn't. That was very fast. And close. But now if we go up to view, we can click on this unsteady flow spatial plot. And then we have the different variables. Now we're always going to have water surface elevation and flow, but then the extra variables that we checked on earlier is here, like lateral flow, water surface air, flow air, depth, and invert. Actually, I don't remember the lateral flow. It's all right. But anyway, we don't have a dozen options. We have about half a dozen options to check from for variables here. Okay, so let's just look at water surface elevation. So if I click the little play bar here on the top right of the window, there's a play button, and then that should simulate the hydrograph going up and down. So clearly this is not realistic. This is not what we want, but it does give you a different view on the results from the compute. I can also turn on like the flow, for instance. Okay, it's still running. Stop it. Variables. Okay, now I've got the variables. I got the flow rate and CFS toggled on here. This is river station 10,000 all the way downstream to river station 0. So starting off, let's just get past the first couple time steps. We're on a 1 minute time step now. I'll click the play button and we'll watch this simulate through. Okay, so the hydrograph is increasing, and here's the flow rate. It doesn't look too crazy except for the very beginning there. But I think what's more concerning is this water surface elevation. I'll go ahead and close that. Also in the view menu, if I select unsteady flow time series plot, we have the time series data for whichever selected cross section we're interested in. The variable we want to select, this is the same list of variables that we saw in the previous results page. And then besides a plot, we can also turn on a table. And with this table, we can also display multiple variables in the same view. They would just get their own separate column. I don't have a lateral structure so that we're not going to see any data for lateral inflow, but we would for water surface elevation error. All right, back to the user's manual. I want to point something out here. This is the page we started on, but if you expand the browser window wide enough, you'll get this menu over to the left, hopefully. And then if you click on Finding and Fixing Model Stability Problems, these were some of the notes I was just referring to, and then click on Computation Level Output for Debugging. My takeaway so far as to debugging in HEC RAS is the results are really never going to tell you exactly what the problem is. It's up to the modeler and up to the modeler's discretion and experience to know what changes to make and just give it a try. So I think experience and a little bit of knowledge will help a long way, but it's not something I can just teach. What I can tell you is basically what it tells me here sort of summarizes that once a location of instability is determined on the profile plot, the cross-section plot can be used to further investigate the cause of the instability. And this is sort of where the user manual leaves me hanging time and again. It just basically gives me ideas of things to try and test, and that's sort of what the message I'm passing on to you guys is there's at least 13 different ideas and things to test from this previous page that we're going to step through one at a time, starting here with the cross section spacing. So right now in this model I have 10,000 feet of total reach length, and the cross section spacing is 1,000 feet. It's a linear interpolation. So cross sections 0 and 10,000 were developed by me, and then the intermediate cross sections here are all interpolated, hence the little asterisk mark, if you can see that. The user manual says that if you have a river reach that's very steep, you may need cross sections as close as 100 feet apart, or if it's very flat, you may be able to get away with cross sections every 5,000 feet apart. But most likely it's going to be somewhere in between, like 1,000, 200, 500. So what I'm going to do here is change the cross-section spacing. Instead of making it every 1,000, I'm going to create a new geometry file, and then it's going to be every, say, 100. So I'm going to go File, Save Geometry Data As. I'm just going to delete a 0 here, so this will be now 100. Okay. So then I'll go Tools, Cross-Section, Within a Reach, Delete. All right, so this is the original with no interpolated cross sections. Now I'm going to add it back in and every 100 feet, and then click interpolate and close. All right, plenty of cross sections now. Let's go ahead and run a new simulation with a new plan using this geometry file. So I'm going to save that geometry data and then go back up to Run Unsteady Flow. It has my cross section of 100 feet saved right here for the geometry file. So I'm going to save that plan. I'll just call it 100 feet now. Okay. Okay. Paste that in. Okay. And then File, Save Plan, and Compute. All right. Let's see what happens. Okay. So that looks like we've got some errors, perhaps worse than last time. Okay. Minimum error exceeds the allowable tolerance. This appears to take place at River Station 4900. And as before, I could go ahead and view results. Let's see, it looks like I left that unsteady flow spatial plot on. So let's go ahead and see what that looks like. Okay, so that was only 4 hours into the simulation. It looks like it failed, which is a little surprising why more cross sections was a problem in this case. Let me go ahead and do the opposite. So I'm going to remove some cross sections. In fact, let me just go ahead and remove all the cross sections, the intermediate ones. So I'm going to save this geometry file, and then I'm just going to click OK for 10,000 feet now. File, Save, and then Tools, Cross Sections. I'll go ahead and delete all the cross sections and OK. File and save the geometry file. Now let's go ahead and run this. So what we're doing is just making it fewer cross sections. Perhaps not enough, but we'll see what happens here. I'm going to save this plan here, and it's going to be 10,000 feet. Let me copy that. Okay. Okay. Let's go ahead and save the plan and run it. Okay, I can't explain that. Looks like there's no errors. I mean, there's a little bit of a volume error, which is just 1.6 acre feet, which is a very small percentage, 0.000128%, and that looks good. Anyway, let's go ahead and look at the water surface elevation, and I'm going to run the simulation here. Okay. So the water surface elevation goes up and then goes right back down, and that's smooth. Back to the user's manual real quick, just to finish up this topic of cross-section spacing. What it provides us is it says you can go ahead and change the spacing down from, say, 1,000 feet spacing down to 200-foot spacing. And this graph will show the resulting hydrograph, and it shows that the values may actually change a little bit. And the question is, how do you know how many cross-sections are enough? And what it says is to continue reducing the spacing between your cross-sections until the shape of the hydrograph does not change, in which case you can go ahead and no longer stop decreasing the spacing between your cross sections. I'm sorry that wasn't exactly consistent with my example, but that's what the user's manual says, and getting examples to do exactly what it says here is I found to be a little bit difficult. All right, let's scroll up here. Number 2 here is the computational time step. The user's manual says that the computational time step should be set such as the current value is at most 1. So let me just scroll down to that section here. Here's the computational time step section. Here's the current value where VW represents the flood wave speed, normally greater than the average velocity. Delta t and delta x is the computational time step and distance between cross sections. So just from this equation alone, where you want this left-hand side to be at most 1, there's a few things we can do. For instance, we can decrease any one of these 3 factors. We can decrease the time step. We can decrease the distance between cross sections, which is what we just did with making the spacing between cross sections less, or we can decrease the velocity of the water, this flood wave speed here, V sub W. This V sub W is calculated down below. It's DADA. I don't know what that means, but further below, you can multiply the average velocity by this factor, 1.67 or 1.44 or whatever, based on the general shape of the cross section. But what we're talking about here is the DT. So what I could do is go back to that previous simulation that did not work for me and then change the computational time step. So what that looks like is, let me close this. I'm going to open up that original plan that did not work for me, which was the 1,000 foot, 1 hour time step, and click OK. Now, when I said 1 hour, that referred to this hour here, which I probably should have made it 1 minute because this is the computational interval that I'm interested in. In fact, I'm just going to go ahead and do that now. File, save plan as, okay, 1 minute, and then click OK. And then I'll just call this 1 minute. Okay. So I know this doesn't work, but if I wanted to save the plan as something else, like with a smaller time step, such as 10 seconds, that would give me 6 times as many time steps and would definitely lower that current number. So let me go ahead and do that. I'm going to go File, Save Plan As. Instead of 1 minute, I'll just say 10 seconds. Click OK, and use the same thing here for the short ID. And now I actually have to make the change. So we'll change this computational interval to 10 seconds, file, save the plan, and let's see if that works. So this does take longer to compute. I've noticed that. All right, so I'm seeing some of the same errors pass by here. Right, so it looks like we still have some problems. And let me go ahead and investigate that. I'm going to go View, and let's look at the water surface profile. And then I'm just going to step through the animation here, manually click through here. Yeah, so this is definitely a problem. You're not going to have this in nature. This is not natural, and there's still some model instability issues that I need to deal with here. In the interest of time, I'm not going to dwell on that or try to figure it out, but I wanted to finish off this exercise by mentioning that there is a practical time step selection where this delta t value, which I started at 1 minute and then just changed down to 10 seconds, is the TR times 20, or time to rise. Below here, it says time to rise of the hydrograph to be routed. I really think there should be a division symbol here, so it's 5% or less of the time to rise. So anyway, let me see what that percent, that delta t would be. If I go to my hydrograph again, and then here's the flow hydrograph, and I'm going to plot the data. The peak of the hydrograph occurs right here at about 6 a.m. on January 2, and then it starts right about here, which is about 6 a.m. on January 1st. So 24 hours, we'll say 23 hours divided by 20 would be 1 hour. So yeah, I think my original time step here, close that. My computation interval of 10 seconds is sufficiently low, and even a computation time step of 1 minute was sufficiently low because 23 hours divided by 20 would still be more than an hour. In fact, just for kicks, let's see what happens with 1 hour. I'm not going to save the plan with a new name or whatever. I'm just going to run this as one final test for this lesson. Okay, so looks like there's still some problems. Clearly, I need to fine tune my model and better prepare the lesson before recording it. Well, regardless, I hope what I provided in this lesson was enough to get you started to understand what it means to have an accurate model and a stable model, and a few things to try if your model is not stable, namely uh, decreasing the spacing between cross sections and also decreasing the time step in your simulation.